an amazing 25 plus years of experience leading teams, development. Jasper, be careful, the microphone's picking that up. All right, and he was on the team that originally founded. Oh, thank you. For like the last 3 words I say. He was on the team that was the original led the effort to originally build the first Java application server. I'd like to have a great big introduction for John Piekos.
Thank you, everyone. Can you hear me okay back there?
Yes.
All right. So a couple of weeks ago, I didn't have any slides, and I said, I got to figure out what I'm going to say down in New York. And so I went on my, I have a bicycle, and I went out to plan a 40-mile ride outside the city of Boston, and figured I'd think about it during the ride. Just so happened it was one of those windy days, and I'm riding into a headwind. It seemed like my whole route was going into the wind. So I said, I'm going to just, make an executive decision, change my course, get out of this wind. Then I came to traffic. We actually have some highways up there. Outside the city, there's no traffic, but the main roads are pretty busy. I want to get away from traffic. That pushed me into the hills of Westford, where I live. And I was really struggling out there. It was a tough ride. Finally finished, made a lot of trade-offs, but to complete the workout. And you're probably wondering what this has to do with VoltDB, but I didn't think anything about the presentation. All I thought about was operating in the constraints of the environment, nature, and cars. And it gave me a feeling of trying to scale a database, similar type of feeling, where you've got existing tools. You like that. You've got laws of physics, you've got existing legacy databases, you've got just constraints, unknowns, like when you're going to get a burst of internet traffic, and you're making trade-offs in your application. Like I made trade-offs in this ride to achieve your business goals, and you're often focusing in on those constraints versus the actual business logic and your actual business. You're spending a lot of effort. So that was my lead-in. I'm going to give you a nuts and bolts overview, give you a demo, and I thought I'd start out talking about some of those trade-offs that today you have to make, which a lot of these are alleviated with VoltDB, and I'll get into that. But the first one is I/O bottlenecks. How many people here add memcached or so we got people nodding. How many people offload reads to a replicated server? So you're reducing the I/O, you're making trade-offs there. Money's a pain point. You often have to throw money at a problem, buy new hardware, scale up hardware, just to solve the scalability concerns. I'm not even going to ask for a show of hands how many people have thrown money at a problem. Data model, we're used to traditionally over the last 30 years a full relational model. But when you start scaling up, particularly at web scale, you tend to not be able to carry that baggage. Facebook is one. I've listened to talks where they've gone to almost a key value store on MySQL, so they've dropped the columns and highly optimized that, spent a lot of effort to get the scalability they have. Some people have gone to a document store just to reduce the overhead of a legacy, they find a legacy database. Transactions is another challenge. Thank you. Yep. So some people will do batch commits or reduce the isolation levels to get throughput. You might give up ACID. You might consider an eventually consistent type system to get the scalability and high availability. Again, these are all trade-offs you're making to achieve web scale. And finally, the biggest one, I think, from my point of view, is application sharding or partitioning. How many people here, is anyone sharding MySQL? Yes, we have a couple. So you're moving a lot of logic that used to be in the database into the application. Your application code is routing the requests and stitching back results to the client. So VoltDB, I don't promise that it solves all the world's problems with scale, but it really addresses some of the core ones. It was actually developed from the ground up to address at scale, hundreds of thousands of transactions a second and to eliminate some of the common hotspots. For I/O bottlenecks, as you know from the quiz, we operate in memory, so we're not reading data from the disk, we're not buffering, we're not locking, we're doing everything in microsecond transactions. We serially execute the requests. I'll have a slide later that shows you exactly how the transactions come through. But we're avoiding locking because we're serially executing in each partition. As far as money goes, we're linearly scale out on commodity hardware or in the cloud, so we don't require specialized hardware. The commodity Linux box works just fine, and you'll see when Ding comes up, he's going to demonstrate tens of thousands of transactions a second on his MacBook up here. We're also one of the lowest cost per transaction databases out there. We have a modified TCC benchmark. You can look on our blog and our community and download it, and you can run that. We also offer open source and commercial licenses. The open source version is quite robust, and we have many people in production with that as well. You don't have to give up your relational model that you're comfortable with VoltDB, and you still operate with the data in a SQL using SQL semantics. Transactions, our core is ACID transactions. It's consistent data, and that's how it operates at its core level. If we can't maintain ACID transactions, we're not returning eventually consistent results. We just we'll let you know. We're also I'll touch base on this later too, but we're fully durable. So when people hear in memory, they think, what happens if the power goes out? What happens if I unplug it and shut it off, or the machine crashes? Will I lose my data? You're not going to lose your data with VoltDB. We do have, as one of the other quiz questions was the snapshotting command logging, and I'll get into the details on that. And the big one, as I said, is application sharding, or sharding in general. That's really the VoltDB, that and in-memory operations is VoltDB's secret sauce. So we'll accept the request, we'll route them to the right place, and we'll stitch the results back together and deliver it to the application. The application, the client, is treating the cluster as a single database. It doesn't need to know where to send the request, it just sends it to VoltDB. So you might think, wow, this is the greatest thing since sliced bread. I'm going to replace all my databases with VoltDB. We're not a general purpose database. What we're really focused in on is the high velocity transactional type of applications. Where you're getting thousands to tens of thousands to hundreds of thousands to millions of transactions a second. We'll stay up in the face of failures. We will do case safety. You can lose nodes if you're case safety, which is essentially replication within the cluster, so it's replica replication. You can lose nodes and still maintain ACID semantics and return results. We support, when you're getting a steady fire hose of transactions, you can manipulate state. So it's not just ETL or just pure ingestion. You can manipulate it using standard SQL requests, SQL queries, or Java semantics as well in the store procedure. And we also provide capabilities. You're in memory, you're bounded by the memory in your cluster. At some point, for some operations, you want to get data out into an NLX package. And we provide the ability to either bulk dump into a Hadoop, for instance, or stream it out to a Hadoop or Vertica. But I would also add that a lot of our customers, a good segment of them, will use us as a database of record to keep the data in memory. Because memory's fairly cheap today. You can store a lot of memory and you can run your business on it. And unless you've got a fire hose app where you're ingesting terabytes a week or a day, there's no requirement that you have to push the data out of Vault as long as you have enough capacity in your cluster. So, I've said the high velocity database. Well, what types of use cases might that entail? I'm not going to read every word here, but you can imagine high ingestion type of applications like financial trade support applications. Cell phone and call data records processing is another big area for us. Online gaming, we've got a lot of multi-users. Yeah. Sure. the question was about the analytics, and I'll talk about the lower frequency operations. So we're ingesting at a high rate across all these types of verticals: online gaming, digital ad exchanges, where you can bid up type of ads, wireless location, or even denial of service, traffic pattern analysis for internet traffic. But the analytics piece of that is sort of leaderboard type things. What are my top 10 players in the game right now? What I can do aggregates and sums of things for like traffic pattern analytics or fraud detection, or what is my current exposure on securities. So we're not talking deep analytics that you'd use a specialized database like Vertica for. So you're talking more of the near real-time analytics where you're tracking the current state of your system. And we'll see, actually, Ning's demo will show a pretty good example of, they'll do some interactive SQL queries, and you'll see the types of things that we consider this near real-time type of analytics. I should say that this is the marketing slide on our verticals. We have other applications, we have a couple that they track runners, or I've done the bike, athletics thing. I'll continue. You put a running chip on your sock or your laces, and then you run over the mats, and it gets your time. And they're running they were logging data for, I think, the LA Marathon this year, and running through Volt, giving leaderboard type of activity there. So what's under the covers? So that was the overview, and I'm going to dive into how we do it. We'll get a little bit more of an overview, sorry. So the origin was an H2R project, which was a joint research effort between MIT, Yale, and Brown University. And actually, Ning's one of the graduate students that worked on it at Brown. But the goal, they measured the overhead of existing databases, and about, I think it was 60 or 70% was latching, locking, just the I/O, and it was the real work that was done was just a fraction of the total time that was spent. So their goal was to eliminate as much of that as possible, and you'll see that coming through. We run in memory, so we eliminate disk I/O waits. We serially execute incoming transactions, so we're not row-level locking. We don't have lock contention. We don't have deadlocks. And the goal was to scale this to web scale. So adding node, linearly scale, add a node, get another 100,000 transactions of capability added to. And again, the secret sauce was partitioning data across the cluster and evenly distributing just both the data and the CPU processing. So diving into partitioning a little bit, we have two types of tables. Your traditional table, which is just, we call it a replicated table, because there'll be a copy of that table on every partition. These are the replicated tables are the smallish tables, the tables that don't change that much, and you want to keep them co-located with your sort of high throughput data, your partition tables. So the partition tables that's the data that you want to shard across the cluster. That's really your fire hose of data coming in. That's your hot data. You want to spread the load across the cluster. Think of session tracking for digital ads. You've got cookies, and you've got millions of users hitting your cluster. Each one's got a session. Each session will hash evenly across the cluster, and you can, in parallel, service all incoming, sort of cookie operations, for example, throughout the cluster. So for you're defining the tables, the semantics of tables in DDL, in SQL. You're loading into Volt, and as data is loaded into Volt or is received from Volt, it's automatically partitioning or sharding the data for you. It's getting the data to its appropriate partition. So you as the client don't really care or don't need to know which partition in a cluster is hosting which data. Volt is doing that all under the covers. So here's just more of a graphical nature. You've got table A, B, and C, and all three of those are partition tables. So horizontal slices of those will be spread across your three servers. And thing to note here is that it's not one partition per server. Our general rule of thumb is a partition per CPU per core on your machine. So if you had 4 quad cores, you might have 16 available processors. You might partition across 14 of them, leaving a couple of CPUs for ancillary operations for the machine. So diving deeper inside a partition, I'd mentioned, I'll stress it again, that it's serially executed. So work comes in, and it's globally ordered in the cluster, and it's also ordered within the partition. And the transactions are executed one at a time, so there's no contention. It's all being done in memory, and you can have a transaction that has dozens and dozens of SQL statements in it, and it's operating in memory at microsecond capabilities. So each partition has this work queue, and it's got an association with the table data and the index data. I would also say that this line is fairly telling underneath the execution engine. We are implemented in Java and C++. So Java is on top. It's a very thin layer. Our storage and memory management is done in C++, so we're not impacted by garbage collection, for example. So we get very even execution speeds. So I hinted at this. A transaction in VoltDB is a Java stored procedure. So to get the maximum throughput, you would build a stored procedure, you would pre-compile it, and you would load it into Volt, and you would invoke the procedure from your client. We do accept ad hoc query. It's in an order or two of magnitude of slower throughput, and we're improving that. But if you really want to scale to hundreds of thousands, you've got you build your stored procedures with as much SQL and Java logic in there as you want. And for instance, one of our TPCC, I think on average we have 26 or 27 SQL statements per transaction, and we're getting upwards of 100,000 transactions a second in our testing with that on a 4-node cluster. So you can imagine stored procedures aren't that restrictive if you're thinking of a Firehose type application. These are regular. You know this is the data coming in, and you want to process it as fast as possible, and you want to sort of enrich it or do something with it. So those are tried and true pathways. Other types of things, like you want to do some leaderboard stuff or some real-time or near real-time analytics, can be ad hoc query type of things. These are less frequent operations. You're imagining you're getting in hundreds of thousands a second of some Twitter feeds or something, and you're periodically doing a dashboard update on what's the current trending topics, or if it's a trade support application, every second, what's my my exposure here on this security. We do have a full set of clients. We publish our wire protocol. We've had the community contribute some of these clients, but our really top tier clients are Java, C++, Node.js with our 695,000 transactions a second, and C#. So we do have PHP is also used a lot, Python, Ruby, Erlang. We have a JDBC driver. If you do want to interact with it through ad hoc queries, you can invoke stored procedures through through JDBC as well. And we provide a JSON API too over HTTP. And I just want to stress that you've got one or more nodes in the cluster. We have clients well over 20 nodes. You don't have to know which node to connect to. Through our clients, you can connect to one node, you can list all N nodes that you have, and the clients will round robin through and skip over failed nodes that weren't responding. So really all you're doing is connecting to the database and you're interacting with it. A little more on the transaction model. So the store procedure invocation will come in, and if I'm updating a cookie, some session data for cookie ABC, Bolt will say, oh, I know ABC's data is on partition 1 or server Y or whatever, and it will route that store procedure, globally order it, queue it up, and these will all execute in parallel. And I'll show an example in a second of some actual SQL, and of course Name's demo, we'll get into the details. It's important to note when you're implementing VoltDB, as I hope all of you will be over the next coming weeks, that For maximum throughput, a single partition transaction allows you to execute, in this case we have 9 partitions. It would allow you to execute 9 concurrently in that fraction of a millisecond. There are other types of requests, we call them multi-partition transactions, and that's where you can see here that partition 5 is the coordinator, and it's going to involve 1, 6, and 8. So it will block those partitions, or sometimes all partitions, until a multi-part gets processed through the system. So we're interleaving the ordering of multi-partition queries with the single partition queries. So these multi-partitions are slightly slower than their single partitions. All right, so here's the example I talked about. In this case, we have customer orders, and we have products down here. The orders, which we know we're going to have millions of orders, is partitioned. And products is replicated. We know, we have a couple of 100,000 products or 10,000 products. So you can see we've got a knife, spoon, and fork for the products table. And that's replicated across the 3 partitions in this example. And we've got a set of orders. And so let's look at when some SQL comes in. In this one, we're counting the number of orders for a particular customer. So we've partitioned on a customer ID, and so you can see it's bolded up there. That SQL comes into Volt, and it says, customer ID, I know that's the partition column. I'm going to route this request to partition 2, and it will service it. The others can be processing other requests for their respective data. We're counting the orders for a particular product, the forks. So we've got to hit all 3 partitions at once. So Volt will push the store procedure invocation to all 3, and it will get the results from each of the 3 partitions and stitch them together and return the results to the client. So the client didn't need to stitch anything together. All that knitting of results was done automatically. Here we are inserting a new order, and it's for customer ID 3, which is in partition 3 right here. And it's a single partition query, so you can see you could be accepting a bunch of order inserts or new orders in parallel with one another, and that's where you get your ingestion, that fire hose ingestion. And the last example here is we're updating, we're changing the name of fork to spork, and we've got to hit all the partitions because it's a replicated table, and we'll update transaction consistent across all and change that. So that shows you the difference between single partition and multiple partition queries. For SQL, yeah.
So when I have a table that is split across multiple partitions, as I am inserting data into the table, how does Volt determine which data to send to which partition? If it doesn't know my range of those IDs, let's say I am splitting on customer IDs.
So the question is if you're updating or touching all partitions or a number of partitions, and you don't necessarily, Volt might not know the partition IDs, what do we do?
Yeah, what is Volt's underlying logic for splitting the data of a single table across partitions? Does it fill up the partitions equally or?
So how do we split up data across partitions? Well, we'll use a hash function on the partition key, partition column, the partition value, to spread the data out automatically. And if you're doing a select star from products, something like that, we would hit every partition and get that data. So yeah, it's evenly distributed with a hash function. And we're looking in the future to do range functions as well, but right now it works pretty well with hashing. And if you choose, it is a good point if you choose a column like, let's say, states, and that's your hash, but most of your data is New York based. You can have a little bit of skew there, and so that's a consideration to choose an appropriate sort of value to hash on that spreads out the data evenly, and thus spreads out the processing across the cluster evenly. So we support a subset of SQL, and it's mainly the online transaction processing, the TP type of SQL. Insert, update, delete, a subset of select with we support the aggregates, counts, max, min, sum, so SQL-like, And we support materialized views using count and sum, which really helps. It helps you to get the leaderboard type queries in a very efficient manner because we're pre-computing some of the common pathways. So we don't have to do a full table scan across all partitions. We're adding SQL all the time. We love your input, but you have Java to do it. You can do a lot in Java in between multiple SQL statements if you need to. So often there's a balance. If you can't do it in a language, you can probably pretty easily do it in Java. But that's something we're focusing on. So we are a transactional database. We're not an analytics database. So you're not going to get the full reporting. If you have a heavy analytics component, historical reporting, we're probably not the right solution. You need to look at like a Vertica or something like that. This steps back to Mike Stonebreaker saying, one size doesn't fit all. And Vertica was the deep analytics tool, and Volt is really the OLTP ingestion database. So we talked about durability in the quiz, but I just wanted to drill this in. Just because we're in memory doesn't mean you're going to lose your data. We have snapshots, and this is available in the open source. You can continuously snapshot your data. It's you can control the f-sync. It's very tunable. We've got a lot of headroom in Volt. It's rare that we see an impact by durability in terms of performance, because if someone's running 20,000 transactions a second, we can do 100,000 on that box. We're really not using the CPU. So essentially what we're doing is, in between snapshots, essentially what we're doing is logging. We call it command logging. And this really is a transaction log. It's a stored procedure invocation that we log. So when we get a request, before we even process it, we throw it into another thread to log. And whether it succeeds or not, because we know it will be deterministic on replay, and we can go and execute the request. And then if you require the highest level of durability, we'll wait till it's written to return the results. But it also depends on the hardware you have. On obviously battery back disks or some controllers will give you faster throughput. But we rarely see an overhead, a noticeable overhead for typical applications of the 50,000, 10,000. 1,000 a second type of applications. Yeah.
Which hardware will be better for VoltDB? Hardware architecture.
Hardware architecture is better for VoltDB. So we run in the cloud. So whatever you get there, you never know. Commodity Linux boxes, a quad-core Linux box is fairly cheap. So those are perfect for Volt. As far as disks and stuff. We work on normal spindle disks fine. If I/O disk I/O for full f-sync, you want to go to an SSD or a battery back cache. But we do have recommendations for spindle type disks, and I don't actually have it here. But we got a write-up that we can send you. You can see me after. But we work in the cloud. We work in the cloud just great, and in fact, that Node.js benchmark was in the cloud. And even with the variable or unknown latency and performance you get from Amazon, we still saw some amazing results. So putting it all together, here's the same cluster diagram I showed earlier. We got 3 servers. A cluster like this, we're probably getting 100,000 plus transactions per node. So we're probably going over 300,000, 400,000 transactions. No case safety, of course. This would be just straight out. You'd half that if you had partition replicas. But we're all in memory, and we have no bottlenecks, so we're just screaming in memory on this data. We've scaled this up in our labs and with some partners to 3.2 million transactions a second on a rack that goes 30 nodes, maybe. I think it was 30 nodes. We're a relational data model, so you're using the queries and just the knowledge you have from the years of the legacy database market. You're not giving up ACID semantics, so you're not giving up consistency. You have full durability, the guarantees that you're used to with your applications today. And the auto sharding, partitioning, is done by Volt, and you can linearly scale out by adding nodes. And it's commodity box that gets you there. So that was the slide portion, and I'd like to introduce Ning Shi, one of my top engineers. He's going to show you an example. It's pretty cool. It's traffic data, as you might guess, and he'll show you from building an application from scratch. You'll get a good feel for how it looks from a hands-on point of view. So thank you.
Thank you, John. All right, so I guess I have to figure out how to do the demo and also hold this microphone at the same time. So the demo is, in the demo I'm going to show you how easy and quick it is to create an VoltDB application and import raw data into the database. And then I'll do, while the data is being imported, I'm going to do some interesting analysis on the data. Excuse me. The data set I'm going to use today. Oh, sorry. Should move the window over. Do you notice that I'm not in mirroring mode? The data set I'm going to use today is traffic data, hourly traffic data published by New York State Department of Transportation. And there were two files. Each has roughly 10 million lines in them. So, where's my mouse? So I'll show you the data format. So the data is from, both of the data are from the year 2008 and 2009. We'll take a look at the data from 2008. They are actually the same format, so we can just look at one of them. So you can see here, the data is a CSV file, and the column, so first the column is the sensor ID, which took the record. The second column and the third column here are the date and time, are the date and time of the record was when the record was taken. Excuse me. The next column is the direction of the data. The next column is the direction of the traffic, and then the next one is the lane of the traffic. The last column here, you can see a lot of numbers over here. This is the most interesting number to us because it records the number of vehicles passing this sensor in that hour. So along with the sensor ID, date and time, and the number of cars passing the sensor, we can do something interesting. So with the data set I've just shown you, we now need to create a schema file so that the database knows what kind of data it's expecting. I've already written the schema file, but it's really simple, so we can go through the schema file here. The first table here we can see here, it's called traffic table. It's the table that's gonna hold all the data we just saw. It has the sensor ID column, record date, time, direction, lane, and this is the count, which is an integer. And then I have an index on the sensor ID and record date column, so that we can do faster lookups if we need to. And then this view here is also on the traffic table. It does some summarization of the data, so that when we actually want to do aggregation on the original table, we can just do it on this view. Views in VoltDB are materialized when you change the underlying table, so we can amortize the cost of aggregation across insertions or updates or deletes. That way we can do fast aggregation and look up on the original table by just querying against this view. Are there any questions so far? Cool.
Is that view static or dynamic?
I'm sorry, what?
Is that view static or dynamic? Because you got count star in there and sum? How often is that view updated?
It's dynamic. So when you change the underlying table, which is the traffic table up here, when you change that table, it's going to automatically update this materialized view.
Like a trigger.
Yes, it's like a trigger. So when you when the trigger is fired, it's going to change this view here. So when you query the view afterwards, you can see the updated values.
Would that be performance issue while you manually that would performance issue, like when you enter pages of records?
The performance hit is very, very small. You can barely notice it on any servers or desktops because it's amortized. And doing those operations in Volt is super fast. It's like microseconds.
What's the size of the data? I mean, I know it's everything, right?
Oh, the files. I can show you the files. So the first two lines over there, it's one of them, the data from 2008 is 552 megs, and the data from 2009 is 669 megs. Yep.
So what's the memory constraints on the size of the data?
So your data has to fit in your memory of the machine. If you have a cluster of machines, it depends on the k-safety factor or the replication factor you choose. You will need the actual amount of memory in the whole cluster to hold that many of copies of data. So now we have the schema, and the next step is to actually create a file called project.xml that tells VoltDB where the schema is and how to partition all the tables, as well as what the procedures are, if there are any. Currently, we don't have any procedures, so there are going to be only two things that are interesting in this file. One of them is the schema path. You can see here, and the other one is how we want to partition the traffic table, which we will partition on sensor ID. So when an insertion comes into the database containing all those values, the database will look at the sensor ID of that insertion and then hash it to the correct partition. Then the record will go into the correct partition instead of going to other partitions. So each insertion is a single partition procedure. Now we have the schema and the project file. We can compile the application into a jar file. So instead of providing VoltDB the schema file and the partition information when you start the database, VoltDB actually takes a jar file, which is a bundle of all the files that describes this project, and then it will just parse all the stuff out of the jar file to initialize the database. Now I'm going to compile the catalog by using the Volt compiler command. The first parameter to it is a directory that will contain the procedure file, since we don't have any that's actually empty. And the second parameter is the project file path. The last one is the actual file name of the result. So the output will go to this traffic.jar file. Alright, so notice the output of the compiler. You can see there's a procedure called traffic.insert that's being created for us by VoltDB. We didn't actually write anything in the files that I've shown earlier. This is a simple insertion, SQL insert statement that Volt generated because it noticed that the traffic table is actually partitioned because we specified the partitioning column in the project file. So Volt noticed this, it will automatically create this procedure for us just in case we want to use it later, so that we don't have to write it by hand. I'm actually going to use this procedure to insert the data from year 2008. Let me start the database now. Inside the bin directory, there is a script called VoltDB that will just start the database for you. All I have to pass into it is the catalog, traffic.jar. Now the database is running. I will start loading the CSV file into the database. So we're working on a generic CSV loader at the moment. It's not released yet. It's actually just a simple VoltDB client that reads from CSV files and insert data into the database using the procedure you specified. I'm going to use that CSV loader. Give the first parameter is the file that we want to insert, and the next parameter is the procedure name. Traffic.insert. Cool, so it's inserting data into the database now. While it's doing this, I will use a utility program that comes with Volt called SQL command, which allows you to execute SQL statements or stored procedures against the database so that we can inspect the data.
Yeah, quick question.
Yep.
So that CSV loader command you just ran, I didn't know which server connected.
So by default, it connects to localhost. That's where the database is running.
Okay.
And SQL command. There we go. So the first question I want to ask about the data is, what are the top 10 top 10 highest daily traffic in 2008? So what I'll do is I have to put down the microphone. Select star from the view. Remember that we have the view doing all the aggregation for us? I'm actually going to use this view. Sensor date, where I setting, and we just want to know the top 10. So the limit 10. There we go. We have the top 10 highest daily traffic sensors in 2008. It's interesting. Notice that this sensor here, 30291, it appeared 6 times in the top 10 list. So I guess it's probably just one of those heavy traffic roads in New York. So it showed up that frequently in the top 10 list. Let's see if it's actually one of those heaviest traffic roads. So the next effort I'm going to do is to show the top 10 overall traffic in 2008. Instead of daily traffic, it's actually by year to date. Oops. I must have missed something. Cool, so you guys are actually listening.
So it doesn't have an implied group by?
I'm sorry, what is What's it?
It doesn't do an implied group by like in MySQL. It'll do an implied.
No, it doesn't do that. Yeah. So here it is. This is the top 10 list of the overall traffic, the highest overall traffic in 2008. We noticed that 30291 was the sensor that we were interested in, but it only showed up at the last row. It's nowhere near the top. Where at the top we have 50062, the sensor 50062, which has almost twice the traffic as 30291. So it's a little bit weird. 30291 showed up that many times in the top 10 daily traffic. However, it's only number 10 in this overall traffic list. So I guess it's probably just had spikes during those couple of days. It's not really a heavy traffic road in New York. In order to convert this, one way that I can do is to look at the average traffic, daily traffic in 2008. So instead of doing a sum, this time we'll change it to average. It pretty much confirms my theory. So 30291 isn't even in the list, but 5062 is. It's actually number 2 here. So it must be that 30291 had spikes in those couple of days. That's why the daily traffic, in the daily traffic, top 10 daily traffic, it showed up so many times. So let's go back to the first result. Look at the top 10 daily traffic list. If you pay attention to the dates, it's actually pretty close together for 30291. Notice it's June 19th, 20th, 17th, and then it's 18th, 26th, and 25th. It's within those 2 weeks that this sensor had a spike on traffic. So you guys lived in New York, you guys all live in New York. Any guess on what could drive so much traffic to the sensor? I'm sorry? Where is that?
When I say United Nations, it's just like summit. Once a year.
Nice guess. So to be honest, I actually don't know. However, I tried to, when I was preparing for this demo, I tried to Google it, but Google didn't really help me figuring out what happened during those couple of days or within those 2 weeks. But I did find something interesting. That sensor is actually close to the IKEA store. I think it's in Long Island, somewhere there. So it could be that IKEA had a sales event or something like that drove traffic there. Let's say if I'm really curious about these traffic spikes and I want to monitor them or be alerted when these traffic spikes happen. One way I can do it is by constantly querying the database and find out if a sensor had a traffic spike during the day. Yes?
I'll wait for you.
Okay. So one way to do it is to constantly query the database, but it's tedious because I have to constantly doing it. Do I do it every second or every half second or every hour? And then when I do it, I have to remove the data or the sensors I have seen before from the result. So it's kind of tedious for me to do. The other way to do it in VoltDB is to actually write a stored procedure to do the data insertion. And then inside that procedure, you can look for sensors that has a traffic spike and then alert you when that happens. I have a stored procedure written just to do that, which I'm going to show here. Oh, it doesn't have. Let me use Emacs so it has syntax highlighting. So what you're seeing here is a whole stored procedure in VoltDB. We can skip all the imports and just go to the content. So the procedure is called insert. And what it does is that it inserts data into the traffic table just like the normal insert procedure, which you can see here, inserting into traffic with the values. And then it's going to look at the view to see if the sensor has traffic over a certain threshold in that day, in the same day. If it has traffic over that threshold and we haven't created an alert for this sensor on that day yet, we will create an alert for this sensor on that day. So all these 4 SQL statements will execute in this procedure as a single transaction. So you get all the niceness of ACID. You won't get 2 transactions working on the same partition at the same time. So when this transaction runs, it runs from beginning to the end without being interrupted by any other transactions. So the threshold I set here is 200,000 cars in a single day. Now, with this new insertion procedure, I'll compile the Java source first so that we have a class file. Now it's compiled and being stored in the OBJ directory. We need to create a table. You just saw in this store procedure, we're inserting the alerts into the alerts table. So I will create this alerts table in the DDL file. Alright, so we have the alerts table containing the sensor ID and the record date. We also have a primary key on the sensor ID and the record date so that there is only one record for each sensor on a given day. After adding this, I want this table to be partitioned the same way as the traffic table. So we will add another entry to the project file telling Volt that this will also be partitioned on the sensor ID. Now, since we have a stored procedure called insert, I will add that procedure to this list so that Volt knows we're going to use that procedure later. Now we are all set. We'll create a new catalog which will bundle up the new DDL and the procedure class file.
Excuse me.
Yep.
Just one quick question. Now
Sure.
that we have about 9 million words of data in the database,
Yep.
is there any way to get an idea of what the memory footprint of that looks like right now?
Yeah, sure. I can just take a look at the, let's see, top. Should be the Java process. Oh, how do I? It's. Let me highlight it. I think it's this one here. This row here. It's used. Yep, about 1.3 gigabytes of memory. So the compiler output, if you look at the compiler output this time, it has created much more stuff than last time. We have the alerts table added to the DDL, and it has created a simple delete, insert, select, and update statements for us, and they're all stored procedures that contain just one SQL statements. Because this alerts table is not only partitioned, it also has a primary key. That's why Volt chose to create the select, update, and delete statements beside the insert statement. And the last, near the bottom, this insert here is our stored procedure, which contains 4 SQL statements. Yep.
Why would we not insert into the previous running instance of why would we create new instance?
No, I haven't created a new instance. I'm going to reuse the old instance. If I switch here, you can see it's still running. What I did was that I just created a new catalog, which just bundles up all the files that the database needs when it starts. Now I'm going to use SQL command to actually tell Volt to pick up this new catalog, and it will automatically pick up the stored procedure and create the new alerts table for us. So the updated application catalog is a system stored procedure that will take a new catalog as well as a new deployment file and then update the database accordingly. The deployment, I haven't mentioned the deployment file before because we're just using a single node database that doesn't need special configuration. It will just start with a single node database on my local host using 2 partitions. That's the default if you don't specify any deployment file. So I'll still reuse the same deployment file, but pass it traffic 2, which is the new catalog. Now the database has been updated successfully. We will have a new table called alerts. And this time, I will use the same CSV loader to load the data from 2009, but using this insert procedure which is created so that we will automatically have all those alerts created for us. Oh, and by the way, something I didn't mention when we were looking at the procedure. The return value here. So if we don't have a record of this, if we haven't created an alert for this sensor on that day before, if this is the first time we create it, this procedure will return 1, indicating that an alert has been created. And otherwise it's going to return 0. So if I'm writing my client application, I will just look at the return value, and I would know that when traffic spike happens, I will immediately get a return value of 1 back without further querying the database. And I don't have to prune the data later if I see, because it won't return 1 anymore if it's for the same sensor on the same day. It will just return once on creation. Now I will load the data from 2009 using the same CSV loader. And in SQL command, I'll do a simple select statement to see if there are any alerts being created. So we can see there are actually alerts being created while the data is being inserted into the database. This is without any work from my end, and then the database will just do this automatically for me. And I'll also have a history of all the sensors and dates when the traffic goes over 200,000 cars in the same day. Yep.
Sorry, just taking a step back here. So when you updated your application catalog, if you were running multiple nodes, that's not going to be the same procedure, or would you have to update it nodes everyone?
So if you have multiple nodes, you will do the same. And that procedure is a multi-partition procedure, which will go to every node and do the catalog update for you. So when that procedure returns, you will know that the whole database has been updated. That's all I have for the demo. I'll hand it back to John.
So, any questions? I guess Rick is going to be the moderator.
Before we go on to the Q&A, first of all, I want to give a big round of applause to both Ning Shi and John Piekos, VP Engineering for VoltDB. And I want to give a great big thank you to AppNexus. If anyone is seeking a new role, please come over here, see Jessica, who is hiding. Can anyone see Jessica? Go talk to her, they are hiring. I want to thank you all for coming as well, and we have lots of cool events coming up as well. And we'll start with the QA. Yes?
So have you guys looked at using JSON rather than XML, maybe the description or processing?
Oh, for configuration?
Yeah.
It is XML. We haven't looked at, the question was, have we looked at using JSON for defining the configuration? We've kicked around various ideas on reducing the configuration, but it's something we can look into.
That's done a few years ago when the VoltDB was
Yeah. We'd like to streamline the whole development process, essentially. We're working towards that. So,
One other point, plenty of extra beer, pizza, I forgot to mention that, sitting right over there.
plenty of extra beer and pizza.
And you had your hand up.
Which products and whose market share would you be targeting?
So that's a good question. So the question is, which products and whose market share are we targeting? I'm not the marketing guy, and I know that the marketing guy is already fidgeting as to how I'm going to answer that. But there's an emerging market here, and it's high velocity data, and there's a lot of new applications there. It really is a new market. I think today people are trying to find their way. They're using Google's Big Table, or they're going to try to put SQL on Hadoop, or we really solve a problem where you can get near real-time massive ingestion and near real-time analytics on a data stream. For more traditional, there's this. Am I going to say names? We've seen we're winning deals against times 10. We're much more value-oriented and much more performant. We're solving a problem that the regular databases can't do today without a lot of sharding or a lot of resources thrown behind it, a lot of effort, and we're solving that with with what we've shown you here tonight. And, we've got a bunch of customers and they're in production now, and people are solving things they couldn't do in the past. One example is applications that all of a sudden have a spike of 25 or 30,000 transactions a second, and it's not all the time, but these are things that people did gymnastics around solving today, and they're getting that with Volt for free. This spike, because they're running normally at 1,000 transactions a second, 500, 5,000. They get these bursts. They don't have to worry about it. The cluster they've got, a single node, 2 or 3 nodes, is solving that problem. They're sleeping well at night, not worrying about having to add servers or having to scale up suddenly based on some unknown surge that's going to happen.
Just before we move on to the next question, one other thing. A few people came in late. If you guys want t-shirts, before you go, they're up here. Only large and XL. You want one?
Yeah, right.
Size large or XL?
He wants to throw it again, so sit down.
There you go, here you go. Here's the throw.
Ooh.
Gotta get to ask a question, right?
Yeah, well, the guy behind you actually had his hand up. So,
Okay.
yeah.
Can you speak a little bit, one of the interesting things you keep talking about or alluding to is this sort of magical way that Volt is able to do sharding and deal with multi-nodal installations. Can you talk a little bit to the sort of timeline of an architecture, someone coming up from 0 volt installation to some minimal architectural deployment that make use of all these magical features? And can you talk to a little bit about how such the auto sharding is done? Because a lot of this stuff takes a lot of design and trial and error to figure out how to basically divide things up, and it seems hard to fathom how this can be done algorithmically and dynamically without any kind of human intervention.
Yeah, so the question really is, how do I get up to speed? How much work does it take to build a VoltDB application? And what decisions do you have to make? And what are the trade-offs? We're not going to take an application that's a J2EE app on ORM that's got massive SQL. That's not that legacy stack isn't our type of thing. But what you might be able to do is carve out a piece of that's your high velocity data. And you as the developer probably know what's my HUD table, what's the data that's coming in fastest, what can't I service fast enough. And that's the data you look at, and you look at, you would understand that data, and you'd say, it's cookie tracking data, or it's machine generated data. I've got some ID on it that would make a good sharding column. And Volt will hash, as I mentioned, the hash on that key. Now, where you get into trouble is you say, this is my customer table, or whatever it is, I'm going to pick that key. That's a careful consideration. That's where you get into trouble, because your data will get skewed in the cluster, so a majority of it might be on one node, or a majority of the processing might be on a couple of, you might have a HUD spot. So it's a combination of looking at your data and looking at the types of queries you want to do on the data and making sure that that's evenly spread out through the cluster. So that is a little bit of thinking, but you know SQL, and you're familiar with it. If you're unfamiliar with SQL, it might be difficult, but you're going to report on the data. You're going to do some sort of real-time leaderboards. So you're going to know those types of sort of reporting queries, and that's where you're going to make sure that you're not skewed. The ingestion, most of the ingestion is single part ingestion. That's all happening in parallel. So unless you've really skewed your data, it'll go evenly within the cluster. But we have samples, and we have a couple of field engineers here tonight, Phil and Banna here, that certainly talk about your individual application and provide help. And we've got a bunch of resources that you can just drop us an email too if you need help. So how reliable or how robust is it? So we've been released in the community for almost 2 years now, and with our enterprise for about 10 months. We're in production at a number of customer sites. We're pretty proud of our uptime, and we haven't lost any data. If people who are worried run with a case safety factor of 1, 2, or 3. We have one customer who's running with, I think, a case safety of 3, which means they've got 3 copies of each partition in memory, and they're doing it in the cloud. So they're not even using command logging. They're using snapshotting, but they're not even using command logging. So with 3 copies of the data, they can lose 3 nodes and still be running. And so it stays in memory, running their business through it. So these are production apps.
How are we dealing with ORMs kind of stuff? So, we have stored as vectors. Is there any serialization, deserialization, overhead? Well, we're talking about transactions now, it's transactions.
Yeah, so the question is, how do we deal with ORMs and serializing the data? Today we don't deal with ORMs very well at all. We're working on a sample application to show that type of modeling. The one thing to be aware of is that Volt doesn't, you saw from Ning and mine examples on the store procedures. The store procedure is the transaction. So if the store procedure completes, it's committed. If there's an exception, it's rolled back. So there's no client transaction control. So your traditional Hibernate with, we're in auto commit mode in essence. So there's no two-phase commit outside of Volt. So it's very easy to map, Pojo to a Volt row and result set. But you're not going to plug into an ORM type of application cleanly because of you've got that legacy stack of two-phase commit. And those applications don't scale to web scale that we're talking about. They might have a pain, I throw numbers of 1,000 a second or 500 a second. We're talking here, hundreds of thousands a second. So it's really a different mindset. But we're working on trying to bridge that and look in future releases.
Yeah. What's the reasoning behind specifying the stored procedures in Java? It seems like it's just string parameterization as far as, or from the examples you showed.
So what was the reason behind store procedures in Java? So the core is written in C++ in memory management, but the layer above is written in Java, so it gave us a container to host Java store procedures. We're working on 2 things in that area. One is making an ad hoc query and multiple query statements, or dynamic SQL, more easily accessible and performant. But we're also investigating other, like maybe a JavaScript layer, so you can have through Node, you can have JavaScript end-to-end. But those are sort of R&D type things right now.
One of the things I remember reading about fairly early on was that schema migration was an issue. What's the current state of schema migration for an online system? And if it's not great, what's the plan to improve it?
Yeah, so the question is my schema migration. So Nick did show you adding a table, but modifying columns in the table does require you to snapshot and stop the database and reload and repartition the data, which is very quick. We've improved that. We do have it in our roadmap to do column type of, to allow adding columns, deleting columns, and the like. None that I'd offer here on camera, but it's certainly drop me an email, come up after, and we can talk.
Can you talk about ECL?
Can I talk about access control? We have a users and groups the specification in our deployment file, and or is it it's deployment, right? Deployment. And I get confused between the project and deployment, which is one of the things we're going to be minimizing. But you can put access on store procedures, so certain users can and can't invoke them. It's not I would, to be honest with you, it's not a world-class security system, but it's enough to get by and protect access to the data, particularly through store procedure access to who you want to access it. Management tools. Yeah, we offer in our professional edition or enterprise edition tools, but we have a user interface that allows you to start and stop, configure clusters, push application catalogs, monitor latency and transaction throughput and the like. We have a jQuery-based lightweight tool in the community We have the enterprise manager and the enterprise kit. And yes, and it's all based on a REST API, so you can, if you've got other type REST tools, those are available to interact with.
Next question. All in the back.
Quick question.
Turning around. Yeah.
So can you dynamically add and remove nodes from VoltDB cluster? And if so, then in your multi-partition case, how do you distribute information about what you're hashing? So where the partitions live?
So the question was, can we dynamically add and remove nodes? Today you cannot. Today you can add a node. You can, if a failed node in the K8 cluster, you can rejoin that, so it can bring it back up to K-safety. But we'll probably do something different with hashing, probably the range type hashing. It's later on. It's very high on our roadmap. Is adding a node on the fly. I would say, I'm the product owner in our Scrum process, and I desperately want adding a node on the fly. But we have so much throughput capability on a small cluster that customers aren't hitting that. And so it's, it's only a matter of time. But today, today it isn't an issue. Tomorrow it may be.
Wait, but it's also a capacity issue.
It is a capacity issue, and that's where we hit it versus CPU. Yep. So I feel the pain.
Last question. I saw that hand go up really quick.
In your performance numbers, are you talking about streaming data into the database, or are just batch and grouped numbers coming in?
So the question is, when we quote performance numbers, is it streaming or batch? It is streaming. So we prefer, if you have a small number of clients, we prefer an asynchronous API. We have an asynchronous API that allows you to keep on firing requests at the database. I think one of the problems people have benchmarking is they're used to a synchronous world and just regular programming, and they'll start up a client with a couple of threads, and they'll just synchronously push data at Volt. And you're really tying up, you're waiting on the socket on the client side, and Volt is doing nothing. So we have demos that we have our voter demo, which is like American Idol, where it votes, very bursty. We fire as much as we can at it, and each transaction in our voter demo, I think, is 3 SQL statements, 4 SQL statements. Yeah, and insert and 3 selects, and that's the one we did with Node.js, and we asynchronously hammered with 40 clients, 30 clients.
30
in the big demo, the 695,000 was 30 clients asynchronously pumping data. So essentially streaming it. Each one was an individual invocation that had 4 SQL statements, and that was the 695,000 a second. And if you download our kit, we have that voter sample. You can run it in Java, and on our MacBooks, you can regularly get like 40,000. These aren't the commodity Linux platforms, but you can run it on the Macs and get 40,000 a second, and you can watch it happen.
Okay, John and Ming will be up here for more questions one-on-one. I want to thank Piekos, NewSQL